Good afternoon. Thank you for attending our Tech Talk. I am Anil Chaudhary, Principal Scientist at Applied Optimization Incorporated. I would like to share with you how you can reduce build defects and microstructure anomalies and achieve higher mechanical properties using simulation of gas flow and metal fusion to predict and optimize processing parameters for the laser powder bed fusion additive manufacturing process. Applied Optimization, or AO for short, is the developer of the simulation software, AMP², which stands for Additive Manufacturing Parameter Predictor. AMP² is useful to expedite production part approval process by predicting part-specific additive manufacturing parameters, eliminating defects in critical regions, eliminating hotspots, obtaining consistent microstructure, meeting stricter acceptance requirements for pre-production parts, verifying part quality is consistent from one build to next. The simulation begins with the prediction of gas flow in the build chamber, which is used to design the scan path to mitigate spatter-induced defects. The scan path is used as input to perform a sequence of analyses that emulate the additive manufacturing process. Layer-by-layer analysis is used to predict residual heat build as a sequence of layers, which are deposited to build the part up to the current layer. Line-by-line analysis is used to predict the residual heat build during the scanning of the current layer. This analysis predicts the thermal transients during scanning. The results of layer-by-layer analysis are used as initial conditions for the line-by-line analysis. The track-by-track analysis performs thermal fluid flow calculations to predict melt pool formation. The melt pool dimensions are used to optimize the values of hatch spacing and the core and contour offsets such that there is adequate fusion between adjacent tracks and sufficient remelting of substrate material. These analyses systematically evolve the thermal behavior of the build and predict parameters that can eliminate defects in critical regions, eliminate hotspots, obtain consistent microstructure, and so on, enabling high-quality as-built material for the part, and consequently, higher mechanical properties. There are two main challenges. The first is to minimize the backlog of sustainment parts. The mechanical properties data for the replacement part should print above the requirements to push the data distribution upwards. For example, if the remaining useful life for the part was 50%, the replacement part should meet requirements for 80% life for the part. Second is to enable the production of high-quality structure-critical parts. The simulation is designed to demonstrate quality material process as defined by the NASA standard, N68335. Its purpose is to reduce risk by attaining highest material quality in high-stress regions, reduce cost by minimizing trial and error, and to enable part production using multiple machines, which is a requirement for C-basis part qualification defined by MMPDS. The technology developed is to predict part-specific process parameters, to eliminate and minimize defects in high-stress regions, and to eliminate microstructure anomalies. Key points on research and development are to compensate parameters for process variability. For example, due to gas flow and laser caustic, we have demonstrated 100 times reduction in build defects and 2.28 times fatigue strength. The Navy requirement is to attain part-to-part consistency. In other words, the 100th part should be same as the first part in terms of its enhanced mechanical properties. Our key innovation is to make this advanced modeling simple enough that advanced degree in engineering is not required. For example, a person with an associate's degree in mechanical engineering can perform the simulation. We reduce defects by 250 times in this complex part that has thin walls, upskin, downskin surfaces, and overhangs. This part, when produced using standard default parameters, had 6,881 defects identified in 20-micron CT scan data. The same part produced using parameter-designed process, using our simulation, had 27 defects. The maximum defect size was reduced 50%. Defects were further away from the skin, and surface defects were eliminated. The part produced using default parameters was 99.9% dense, and the part produced using parameters predicted by AMP² was 99.9998% dense. We achieved 2.28 times fatigue strength for a structure-critical part. We designed fatigue samples to match thermal history during deposition to match the part. Its objective was to build the fatigue sample with microstructure and texture like the part. We built and tested the thermally equivalent fatigue samples to verify superior fatigue strength. We then built the part and demonstrated higher fatigue strength for the part. The key feature of the simulation is to reduce the cost for the additive manufacturing process, pre-qualification, by 40% or higher. This savings is due to the quicker development of quality material process, as per NASA standard 6030, whereby we characterize process variability and use simulation to compensate for the process variability, allowing the production of parts with consistent quality across the build plane. The simulation-designed process parameters are useful to reduce defects and achieve higher mechanical properties. This slide shows a link, which is a structural part. We reduce defects in this link by greater than 13,000 times using process parameters predicted by the simulation that is AMP squared, as compared to when the same link was produced using default parameters. The default link has greater than 19,000 defects identified in the 20-micron CT scan data. The link optimized using parameters predicted by AMP squared had 14 defects. These parts are currently being fatigue tested to demonstrate superior fatigue performance. The technology is a scientific method to produce parts with higher mechanical properties. There is a need to produce such parts much beyond the Phase 2, for example, by PMA 299 for the H-60 multi-mission helicopter. We have implemented AMP squared on the Navy computer systems and are working with our TPOC to schedule training for users at NAV Air and the Naval Air Warfare Center, who are our current transition advocates, along with an aerospace OEM. We are looking to position this simulation for technology insertion, for example, via Phase 2.5 or Phase 3. Its objective is to reduce the time and cost for the additive manufacturing process pre-qualification for complex structure-critical parts. The marketplace for this simulation technology is growing both in the DoD and commercial arenas. We may ask, why do we care to reduce defects when we hot isostatic press the parts to heal defects? It is better to have no defects than to heal defects. Also, hot isostatic pressing cannot heal surface defects, and not all alloys can be subject to hot isostatic pressing because this process results in reduced strength. The simulation is designed to produce higher quality parts. It aims to achieve mechanical properties data one level above the requirement and push the data distribution upwards. Also, the metallic materials properties development standardization requirement for part qualification is to demonstrate ability to produce quality parts using multiple machines. This requirement is difficult to fulfill without the use of simulation to design the process parameters and to understand causality of any potential differences between machines. We can help reduce schedule, cost, and risk to achieve higher mechanical properties for your complex, structure-critical parts. We can demonstrate reduced cost and time to achieve additive manufacturing process pre-qualification. Our business model is to use our simulation to predict part-specific parameters, compensate for process variability across the build plane to produce consistent quality parts, and to demonstrate higher mechanical properties. At Applied Optimization, we have the right balance of nonconformity and critical thinking, for example, by developing advanced process monitoring to verify that part quality is consistent from one build to the next. We have developed optical hardware to enable fine resolution, track-by-track, simultaneous imaging for visual inertial system, and mid-wave infrared for every part on the build plane. Please see the high-resolution melt pool mid-wave infrared images collected using this optical hardware. Please come to our display booth to see demonstration of the simulation technology AMP squared software and assess the test samples. We look forward to working with you to reduce the cost and time to develop quality material process for your part. Thank you for your time and attention. We appreciate it.